In calculus, it is important to be able to determine if a function is continuous or discontinuous. So our goal today is to look at functions and determine their continuity. A function is said to be continuous at a number a if and only if the limit as x approaches a of f of x is equal to f of a. In order for a function to be considered continuous, we have to prove three things. The first thing we must prove is that a is in the domain of f. So we must prove that a is in the domain of f. So there cannot be vertical asymptotes at a. There cannot be removable holes at a. The second thing we must prove is that the limit exists. More importantly, when we're proving the limit exists, is basically showing that the left-hand limit is equal to the right-hand limit. The final thing you have to show is that once the limit exists, the limit is equal to the domain value. The limit must be equal to the domain value. A function is not continuous from both sides if it is not continuous from one side. Functions can, however, be what we call left-hand continuous and right-hand continuous. So a left-hand continuous function has the limit as x approaches a from the left of f of x equaling f of a. And a right-hand continuous function has the limit as x approaches a from the right. So left hand is where you have a with a negative, right hand is a with the positive. Functions can be continuous on an interval. Functions can be continuous on an interval. So if it is continuous at every point of the interval, then it must be continuous at the endpoints. And then we can say that it is right or left-hand continuous. All right, so here are examples of continuity versus discontinuity. If a function f is not continuous at a point C, then we say that f is discontinuous at C. C is known as the point of discontinuity. And we talk about all the different types. So one type of discontinuity is called removable. Removable discontinuity occurs when there is a hole in the graph. So removable discontinuity occurs when there is a hole in the graph. Holes often occur when you factor the numerator and the denominator, and a factorization can cancel. A hole occurs when you can factor the numerator and denominator, and two factors cancel. infinite discontinuity. Infinite discontinuity occurs at vertical asymptotes. Infinite discontinuity will occur at vertical asymptotes. Jump discontinuity. Jump discontinuity is an example of discontinuity in which you have a piecewise, but the piecewise doesn't fill in the hole. So here's a piecewise function. This has removable hole up top, but then at x equals 2, f of x is 1. So 1 doesn't fill in the hole. Therefore, this has jump discontinuity. A step function is also an example of jump discontinuity. Jump discontinuity is basically when you have to jump from one function to another. You must be able to correctly label discontinuity types. You must be able to correctly label discontinuity types. Questions at all on those? Okay. So it says, given the following graph of f of x, at which values of f of x is the function discontinuous, and what type of discontinuity is occurring? So we're looking for two things. We're looking for the points of discontinuity, and then we're looking for what type of discontinuity they are. So this graph has discontinuity at 1. And it's removable because you have a hole. We have discontinuity at x equals 3 because the function jumps. And we have discontinuity at x equals 5 because, again, you have a hole on your graph, but you jump to a spot and jump back down. Okay. The greatest integer function is an example of a step function. So a step function will have discontinuity at every step. The greatest integer function is a function in which no matter where you fall, so if you're talking about from 1 to 2, the greatest integer function says that 1.1 will always go to the number 2. If you're talking about a number from 0 to 1, then it would always be the number 1 because 1 is the greatest integer. So if you looked at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right, the greatest integer function is kind of like the double bar bracket. So the greatest integer as x approaches 2 from the left would be 2. The greatest integer as x approaches 2 from the right would be 3. So, does the left-hand limit equal the right-hand limit? Does the left-hand limit equal the right-hand limit? No. What would f of 2 be equal to? It does. So f of 2 would actually be 2 because it's a closed circle at the end of the bar. The limit does not exist. Sorry. So the limit as x approaches 2 of the greatest integer function does not exist. F of 2 is 2. So the integer function is what we call continuous from the right. And then the function has what type of discontinuity then? It's going to have jump discontinuity at every integer. Okay? Show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to 1. So the first thing we have to do is talk about what this function means, looks like, etc. So again, anything to the 1/2 power really represents a radical. If you rearrange this, it's kind of like negative the square root of 1 minus x squared plus 1. So we know that a plus 1 shifts the graph up 1 unit. The negative tells me that it's reflected, or it's the bottom part of the square root. The square root of a square tells you that it is a semicircle. So again, this graph is going to look like a semicircle. The domain comes from the concern of what's under the square root. So we would say that 1 minus x squared has to always be greater than or equal to 0 because we know that we cannot have a negative value under a square root. So then I get my points of concern as 1 and -1. And since it's an inequality, we have to check to see if the domain lives between or around. So in this case, since it's 1 minus x squared needing to be positive, if I plugged in -2, -2 squared would be 4. 1 minus 4 is a negative. Plug in 0. 1 minus 0 is 1. 1 is greater than or equal to 0. Plug in 2. It's negative. Since the inequality is greater than or equal to 0, my solution comes from the positive part, which means my domain is the interval given, -1 to 1. So part of showing continuity is showing that it exists on that interval. The next thing we have to do is show that the endpoint values. So I need to know f of -1 and f of 1. So in order to be continuous on an interval, it needs to be continuous at the endpoints. So I need to know what f of -1 is and f of 1 is. So your square root becomes 0. But then it's negative the square root of 0. So it's still 0. So then you add 1 for the shifting up 1, and you get 1. So if you're talking about continuity on an interval, it only needs to be left and right hand continuous inside that interval. So that means I need to look at the limit as x approaches -1 from the right, because that's inside. And I need to look at the limit as x approaches +1 from the left. So again, as you're getting closer and closer to that endpoint, we can even see here down on the inequality number line, since it's a closed circle, you can just plug in the limit from the left and from the right, and we see that both of those are 1. So we've shown that the left-hand continuity is equal to the left-hand endpoint. The right-hand continuity is equal to the right endpoint. Therefore, f of x is continuous on the interval. Okay? Find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right, the left, or neither? Sketch the graph. So the first thing I would do is probably sketch my graph so that I can see the discontinuity, etc. So the top function is x plus 1 for x values less than or equal to 1. So that means I need to start my graph at 1 on x. So I'm going to plug 1 in for x, and I get 1 plus 1, which is 2. Since it's less than or equal to, it's closed. So I have the point 1, 2. represents a linear function with a slope of 1. So I can go backwards, down 1, left 1, down 1, left 1, down 1, left 1. Since it's all x values less than or equal to 1, there is an arrow pointing to the left. Okay, the middle function starts at 1 and ends at 3. So if I plug in 1, I get 1 over 1, which is 1. So that means this graph has an open circle at 1, 1. If I plug in 2, I get 1/2. 3 is 1/3. So the graph is down there from 1 to 3. And then if you look at the last equation, it starts at 3 and is closed. So 3 minus 3 is 0, square root of 0 is 0. So you have a closed circle at 3, 0. Plug in 4. 4 minus 3 is 1, square root of 1 is 1. So then you have the point 4, 1. And then I would plug in 7, because 7 minus 3 is 4, square root of 4 is 2. So that would be the point 7, 2. And we can see our square root function. So each of these graphs produce a different shaped graph. Upon producing it, I notice that I have 2 points of discontinuity. So f of x is discontinuous at x equals 1 and at x equals 3. Both of these are jump discontinuities. And then it says, at which of those numbers is f continuous from the right, left, or neither? So we have to look at the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. Come on. So the limit as x approaches 1 from the left is 2. The limit as x approaches 1 from the right is 1. So again, we already knew it had jump discontinuity, so that's why the left-hand limit doesn't equal the right-hand limit. But it wants to know from which direction is it continuous. Well, the left-hand limit is equal to the function value. So we say that x equals 1 has jump discontinuity, but at x equals 1, it is continuous from the left. Then we would also do the same looking at the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. So from the left, it's equal to 1/3. From the right, it's equal to 0. And we're comparing that to f of 3. which we would get from the closed interval, which is 0. And over here, we were comparing this to f of 1, which is 2. So then we say at x equals 3, it is continuous from the right. Are we okay? That's a lot to take in. So you have jump discontinuity. However, jump discontinuity can have continuity from the left or from the right. And in order to find that, you have to find the function value at that point and compare the left to right hand limits. Does the function have removable discontinuity? If the discontinuity is removable, find a function g that agrees with f to make it continuous. So what we're going to do is basically take a function and construct another function to fill in the hole. In that direction, those should all be -2, sorry. So try to find f of -2. So when we try to find f of 2, we get 0 over 0. So what that tells me is that f of -2 is undefined, because we're not asking for the limit, we're just asking for f of -2. It's undefined. So then if we look at the limit as x approaches -2, we know that in order to find the limit, if we get 0 over 0, that's known as the indeterminate form. The indeterminate form tells me that I can factor or simplify in some way to find the limit. So in this case, we're going to factor the top so that we get x plus 2, x minus 4. So the quantity x plus 2 cancels, creating that removable discontinuity. So then you get the limit as x approaches -2 of x minus 4, which then you plug in your -2 and you get -2 minus 4. So we see that the limit as x approaches -2 is equal to -6. If the limit is equal to -6, in order to make this continuous, we need the limit to equal the function. So in order to make it continuous, I need the limit as x approaches -2 of f of x to equal f of -2. In order to be continuous, the limit must equal the function value. Well, currently f of -2 is undefined, but the limit is -6. So that means that I need f of -2 to also equal -6. So it says find a function g that agrees with this. So we're going to say that g of x is equal to the original function f of x for all x values except -2. And that when x equals -2, what do I need g to be? What do I need g to be at -2? Yeah, I need g to be -6. I need to be able to fill in that hole. So the limit as x approaches -2 is -6. Now, f of -2 fills in that hole with a -6. Therefore, g of x represents the continuous function for f. So let's summarize everything we just said. In order for f and g to be continuous at a and c, you have to have some constant to fill in that missing hole. It is important to recall all polynomials are continuous everywhere. All polynomials are continuous everywhere. Polynomials are x squared, x cubed, x to the 5th, all of those things that are summed up together. A polynomial, by definition, has no fractions. Polynomial, by definition, has no fractions, no radicals. So square roots are not considered polynomials. Rationals are not considered polynomials. And exponents other than whole numbers are not considered polynomials. A rational function is continuous anywhere it is continuous on its domain. So for rational functions, you have to look at domains. And then square roots are always continuous on their domain. So down here, it's talking about other types of functions. A radical function is always continuous on its domain. A exponential is continuous on its domain. And a logarithm is continuous on its domain. Okay, textbook problems.